Hey ho guys, and welcome to our presentation about Markov chain Monte Carlo with Metropolis-Hastings-Sampler Part 1 Introduction. So why should I care about this? Why should you probably watch that video? Well, we will marry two powerful concepts in mathematics today: Monte Carlo and Markov chains. Monte Carlo is often used to find out about values of some weird integrals like this one here, and this is often called numerical integration. And the Markov chains, they are often like processes, stochastic processes, which can only take certain states, and they have transition probabilities which fulfill certain properties. Okay, so first the bright. What is Monte Carlo? So for example, we have this integral which looks pretty disgusting, and with partial integration or substitution, which we will probably learn in university, you will get exactly this: a lot of paper, wasted paper in your garbage bin, because you will not succeed in actually computing this integral. So people use Monte Carlo, so they realize, oh, if I just put one in there, I multiply this whole bunch of terms with a 1, and I realize, okay, the boundaries of the integral are just from 0 to 1. Then I realize, okay, that is actually just the density function of f of uniformly distributed random variable over 0 and 1. And so I have basically an integral like this, which is like a expected value of a random variable which is uniformly distributed. So you can use the law of large numbers in order to numerically compute the value, and this is done with the following theoretical algorithm. You just generate, for example, 10,000 random numbers drawn from U01, and then you get those 10,000 random numbers and you just average them. And in R, you could do it like this: find out what you generate with the help of RUnif. Then you store the values of the function in Gx. You compute the sum and average them. And then you get as a value approximately of this ugly integral we had before, that it is equal to approximately 0.54. Yes, so that's always the first step in a theoretical algorithm of Monte Carlo, generating the random numbers and then averaging and using the law of large numbers. But today we will not draw from uniformly 0-1 distributed random variables, but we will, or we try to sample from a so-called stationary distribution of Markov chains. So this brings us actually to the groom. So what are Markov chains? So as an example, assume that a student can only do either of the three following activities during a day. He can either sleep, eat ice cream, or run. So the states of our Markov chain would be those three. And for example, on Monday he could sleep, on Tuesday he eats ice cream, and on Wednesday he runs. And for example, on Saturday maybe he eats ice cream again. And what makes this a Markov chain would be if the probability that I transit to another state only depends on my current state. So for example, if the probability that the student will run on Wednesday is only dependent on that he was eating ice cream on Tuesday and not that he slept on Monday. And often you can draw a transition diagram like this for Markov chains, and those then are called the transition probabilities of the Markov chain. And if we monitor the student's behavior for a long time, maybe we will notice that the probabilities that the student sleeps, runs, eats ice cream or runs do not change any longer. So we say that the Markov chain has reached a stationary distribution actually. So for example, maybe he sleeps with a probability of 40%, eats ice cream with a probability of 30%, or runs with a probability of 30%. And from this stationary distribution, we want actually to sample for our Monte Carlo simulation. So if we put everything together, what is our goal? What are we aiming at today? Is that if we consider again our beautiful couple here, they have a goal in integrating some weird or disgusting integral maybe. So we have the bride, which knows how to do Monte Carlo with step 1 generating random numbers, step 2 averaging and using the law of large numbers, which looked like this. Where we only have maybe to think about a little bit that we actually have dependent random numbers now, so we don't leverage like the original or the most known version of the law of large numbers, but some different one, but it still works. We still have this convergence, although we use dependent random numbers now when we are considering a Markov chain. So how do we get the samples of our fx? We will just use Markov chains and they are stationary distribution fx. And we will today answer in all the following 2 videos. We will answer the 3 questions. How can we simulate samples from this stationary distribution of a Markov chain? Secondly, how can we program the algorithm in R? And thirdly, how do we determine whether the algorithm does its job or not? And we will do this with a so-called Metropolis-Hastings-Sampler. There's more than just the Metropolis-Hastings-Sampler to generate something from the stationary distribution, but this is what we will focus on today. So, see you in the next video then.